So with that, let's get started. My name is Todd Stauffer, and what we're going to talk about today is the ISA 18.2 standard, a new standard in the area of alarm management. A little bit about myself. I'm the Director of Alarm Management Services here at Exida, and I was actually heavily involved in the creation of the ISA 18.2 standard as an editor for some of the clauses and also a voting member for the committee. So let's take a look at the structure of what we're going to talk about today, and it's going to be focused on alarm management in general and the ISA standard in particular. So we'll talk about why alarm management is important, what are the common alarm management issues that folks face and how do you fix them by following the standard. We'll also talk about why you would need a standard and what the standard is about, and we will kind of do a step through the standard stage by stage and take a brief look at what each part of the standard talks about. And we particularly want to focus on how the standard will affect folks in the process industries, and then also talk about how you would get started adopting the standard or moving forward with it. So let's first talk about why alarm management is important. For folks in the process safety world, you're probably aware of some of these accidents or famous news stories that I've shown on the slide set here. These are some of the most famous process safety accidents in the history of the industry, and one of the common threads between them all was that poor alarm management was cited as one of the most significant contributing factors for every single one. So process safety and alarm management really go together, and poor alarm management can definitely affect the viability of a safety systems operation and safety at a plant. Let's take a look at one of these, and that is the explosion that occurred at the Texas City Refinery in 2005. This took place after a maintenance shutdown for about a month, starting up the refinery. What happened was that the isomerization unit basically overflowed into the adjacent process downstream into the knockout drum, which wasn't designed to take the load of hydrocarbons that it did, and it basically overflowed, releasing hydrocarbons into the air, which were ignited by an ignition source. Obviously a very catastrophic accident in terms of the damage, economic damage, and the cost to people and equipment. We can learn a lot from the investigation or the results of the investigation, though, and we can see, as it is in most of these catastrophic events, that it's not one thing that goes wrong, it's a series of things. And if we understand that, we can work to try and correct them and make sure that we have the things in place to prevent them from happening. So let's take a look at some of the things that they learned, published in the Baker Report, when they investigated the refinery explosion. In the tower, they found that the transmitter that read the tower level actually provided a false reading. It did trigger an alarm, but as the tank continued to fill and basically filled beyond the range of the transmitter, the presentation to the operator showed that the tank level was actually going down, when in fact it wasn't. It was going up and filling to the top. An alarm was generated, but the operator was obviously confused when you look at the screen and you see that the level is going down, but yet you have a high level alarm generated. Additionally, though, there was another alarm there. There was a safety alarm, which you would expect to be there to trigger just in case the operator is not able to deal with the situation. Unfortunately, that safety alarm in the tank level failed to trigger. So there's two potential things that went wrong. Additionally, when you move downstream and you look at the knockout drum, that also had a high-level alarm, which unfortunately did not trigger as well. Now, some of these, particularly the safety alarm for the tower, that had been identified as needing maintenance, and there had been some problems associated with that. Now, unfortunately, before the startup of that unit, the pre-safety review, those devices were not checked. Those alarms that were critical to the safe operation of the unit, unfortunately, were not checked to make sure they were working. One of the other things they cited was that the operators really weren't trained in how to respond to these situations, these upset situations. And another thing that they highlighted, and this is a common situation or a common finding in these type of accidents, is that the HMI display really didn't provide the operator with the information he needed to understand what was going on, which we call situational awareness. We talked about how there was a misleading level measurement in the tank. Well, you might expect that on a well-designed display, there would be other information as to what was going on in the process that might trigger the operator to think that something is going on differently than what that level measurement shows, or that there might be something wrong with that level measurement. If you're seeing a flow coming into the tank, a greater than zero flow rate coming in, and your level is going down, then you potentially know that something is not working correctly. And of course, from that, we also know the importance of alarms in the world of safety as a layer of protection. One of the first layers of protection in the effective design of a safety instrumented system. But poor alarm management doesn't always result in catastrophic accidents. In fact, for most companies, it results in other problems, more along the lines of reduced product quality, potentially damaging production assets, and where it really shows up the most is in the loss of production or downtime. There was a study that was done by ARC a couple years ago that estimated that over $20 billion is lost every year in the U.S. to unplanned downtime. And the really compelling part of that study was that 40% of that was estimated to be from preventable human error, such as the operators responding incorrectly. Now, this is not an indictment of the operator person itself, but more of the system that's working in combination with the operator. And then we have some other metrics here talking about the cost of alarms and poor alarm management in a refinery. Basically, a shutdown of a refinery is instantly going to cost millions of dollars for what it takes to restart that unit. And in a batch process, a deviation alarm may cause the batch to need to be thrown out or downgraded in its product quality, reducing the potential that that product can see on the market. So now let's talk about, in plants that you might be familiar with or situations that you might be familiar with, what are the most common issues related to alarm management? And this will also let you know whether you're a good candidate to really start looking into the ISA standard and starting to follow it. So let's look at what are some indications that you have alarm problems in your plant. And this is just a subset. There are plenty more, I'm sure, and you guys can probably think of other ones that are not on this list. One of the most common is when you walk in a control room and you see that the operator is sitting there, as we show in this picture, with his feet up on the console, maybe or maybe not eating donuts, with alarms displayed on the console and nothing going wrong, nothing being done. So the idea that you have alarms displayed even when there is nothing wrong in the plant is a warning sign. Another warning sign is that you have a small number of points or tags that generate the majority of your alarms. And this may be because they go in and out of alarm frequently in a short period of time, nuisance alarms or chattering alarms. You also may find that when you have a minor plant upset, it generates a pretty large amount of alarms that makes it difficult for the operator to understand what to do. In a worst case scenario, in a real significant plant upset, you may flood the operator with so many alarms that he really can't respond and he doesn't know which ones are important. One of the other major accidents that occurred in 1994 at the Milford Haven Refinery in the UK right before an explosion that occurred, the operators were inundated with 275 alarms in an 11-minute time span. You can imagine if you received 275 email messages in 11 minutes and needed to sort through all of them and figure out which ones to respond to, realizing that some of them are safety critical. It's an impossible task. We'll also look at the operator's performance. Does the operator ignore alarms or miss alarms? Are there some where he really doesn't know how to respond or what to do? Or maybe there's not enough time for them to respond correctly. And one of the other telltale signs of issues related to alarm management is if the operators are allowed to change the limits or the settings from shift to shift. Are they allowed to change it to what they want? Enable or disable alarms themselves or change the limits without authorization. Because of all those reasons, the process safety accidents that we talked about and those common alarm management issues, in the U.S., the ISA 18 committee went to work in 2003 to create a new standard on alarm management, which was completed and released and approved in June of 2009. And it addresses everything you need to do in terms of design, operation, maintenance, management of alarm systems in the process industries. It builds on the work of other recommendations from international sources, such as the EMUA 191 guideline, ASM guidelines, the NOMORA guidelines. One of the major differences, though, between those sources I just mentioned in ISA 18.2 is that the ISA is a true standard. In terms of a standard, it contains verbiage that tells you what you must do. The requirements and recommendations are clearly spelled out in the ISA 18.2 standard. These other sources contain a lot of great information, best practices information, but they're not formulated in the form of a standard that demands compliance. We did take a lot of the best practices information from these sources and build it into the standard. So you'll find tremendous consistency between them in terms of definitions and settings and recommendations. There's, for the most part, no changes to what's been recommended before, but again, the standard defines what you need to do in terms of requirements and recommendations. If you're familiar with the functional safety standards, ISA 84 and IEC 61511, you'll notice a similarity in the approach, and that is alarm management, we take a life cycle approach. It's a continuous activity. It's not a once and done activity. It requires continuous attention. So just like functional safety, we take a life cycle approach in the design of the standard. Now, also similar to functional safety, it's expected to be accepted as good engineering practice by insurance companies and regulatory agencies such as OSHA. One of the things that the standard is designed to do, in addition again to taking that life cycle approach, is to take the most common alarm problems and make sure that they are addressed within the standard. So the standard really does provide the blueprint or a cookbook on how to solve the most common alarm management problems. And here I've listed what some of those are and the different stages of the life cycle where recommendations are provided on how to address them. So now let's take a look at the standard and let's dive in. If you're familiar again with the functional safety life cycle, you'll see a lot of similarity in terms of stages, where the output of one stage of the life cycle feeds into the next in terms of an input, and it is an iterative life cycle type approach. So let's look at the first stage of the alarm management life cycle, and that's called the philosophy stage. What goes on here is the creation of an alarm management document called the philosophy document that will define the standards for how a plant or site will do alarm management throughout all the life cycle stages. So that means it'll define what rules you'll use to prioritize alarms, potentially what colors you'll use in the HMI, and all that kind of good stuff. It's really important that this philosophy is written down so that later on there's a lot of consistency that will be derived in the approach to alarm management. That all starts with the creation of this philosophy document, which was really the foundation of good alarm management. For new plants, it's recommended that the alarm philosophy document be fully defined and approved before commissioning begins. One of the key parts of the philosophy is definitions, and here's the definition of an alarm according to the ISA 18.2 standard. An alarm is an audible and or visible means of indicating to the operator an equipment malfunction, process deviation, or abnormal condition requiring a response. Emphasis on the words requiring a response. Seems like a pretty simple concept, but from it we derive the cardinal rule of alarm management, which says that an alarm is used to indicate a problem that requires an operator response. The corollary to that is if you walk into the control room and you see that there's an alarm on the console and the operator is not responding to it because nothing really happens or nothing really goes wrong, then that point should not be an alarm. And this philosophy, this basic philosophy of what an alarm means and what should happen, is really a guiding principle that we use throughout alarm management. And we hold up this principle throughout the phases, the stages of the alarm life cycle to make sure that we're doing the right thing. In fact, this adhering to this principle and always thinking about what would happen if this alarm is not responded to, or does this alarm really indicate a problem that the operator must respond to, and have we defined what the response is? Is there something they can do? This really dictates or will address many of the most common alarm management issues. So just sticking to this core philosophy or this core tenet of alarm management will eliminate many of the most common alarm management problems. Other things that go in the philosophy, again, this is a document. It's going to describe the roles and responsibilities and really define the guidelines or the standards that you will use for the different phases or stages of the life cycle. Rationalization is a very important one. We'll talk about that in a second. But in that, we want to define what are the rules that we'll use for prioritizing and classifying alarms. We'll talk about what colors we're going to use in the HMI and enunciation for indication of alarms to the operator. We're going to talk in particular about how to treat highly managed alarms. Within the ISA 18 standard, highly managed alarms is the term that's used for safety alarms would be considered a highly managed alarm. It's alarms that require special attention, basically. The philosophy will also contain, information on how you will test and train and the frequency for when you'll do that, what process you'll use for management of change, who's allowed to make changes, what process needs, what authorization and review process is necessary to make changes to the alarm configuration, and also a definition of their performance metrics. What are the targets for what you want the alarm system to, how you want it to perform? And by this I mean the number of alarms that are presented to the operator, the number of nuisance alarms, and all that kind of good stuff. Because we're going to show later that in the life cycle we're going to measure those things. We're going to benchmark against what we said we wanted to achieve. The next stage of the life cycle is called alarm identification. And this is where we're using the various documentation sources that go with a plant to identify potential or candidate alarms. So we could get this from reviewing P&IDs or process hazard analysis or HAZOPs or LOPAs, quality reviews. All these different sources of plant design activities and documentation are the source of identifying potential alarms. And here's an example showing the results from a HAZOP, where the analysis is showing the indication for alarms to help as part of the safety instrumented function. So here's an example of where a HAZOP is used to identify particular alarms. Some of the other information that's in this HAZOP such as the cause and consequence, is also very valuable and will be used in the alarm management lifecycle. One of the things that you're going to see is that the process we are using here is we are looking at the documentation for the plant and understanding the process to figure out what points should be in alarm and why. That's the opposite of the work practice that occurs for many projects, which is often, if the DCS provides all these alarms, let's enable them all and give them appropriate limits or set default limits. So for example, most control systems provide 5, 6, 7, or 8 alarm types for a simple analog indicator. So you may have high, 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 low, 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 rate of change, bad quality, etc. In many projects, people would enable all those alarms. They're free, right? No cost to enable all those alarms. Well, when it comes to alarm management, more is not better. Many people will do that. They'll enable all those alarms, and then they'll set the limits not based on process dynamics, but just using a rule of thumb like let's set the high limit at 90% of engineering range, and the high limit at 80%, and the low at 10%, and the low at 20%. This way we end up with a whole bunch of alarms that the limits are not set based on true process conditions, and the alarms aren't actually necessary. What we're going to see in the next phase of alarm management, called rationalization, we're going to review every potential alarm and analyze and justify and make sure that it truly needs to be an alarm. So for that analog indicator, we may find that, hey, we only need a high alarm in this one particular scenario. We don't want to enable the high, high, low, and low, low, because we might end up with multiple alarms that are triggered for the same one situation. That's another cardinal rule of alarm management. When a problem occurs, you get one alarm. Triggering multiple alarms to indicate the same problem just creates confusion for the operator. So again, during rationalization, we're going to take a systematic review of the alarms to make sure that they truly deserve to be alarms or should be alarms. We're going to analyze the limits, set the priorities. Now, this is typically a team activity facilitated by an alarm expert. If you're familiar with HAZOPs, it's very similar in terms of the workflow structure for an alarm rationalization. Now, also with HAZOPs, in this case, there are tools available that help make this process go smoother and quicker, and can also make it easy to document the results. And if you're dealing with a big system with thousands of alarms, then using a tool can really cut down the amount of time it takes. In rationalization, the goal is really to create the minimum set of alarms that are needed to control the process and keep the plant safe. Again, more is not better. We just want the most significant and most necessary points. And what we're going to do in terms of a workflow process is we're going to take each alarm and say, okay, what would happen if this alarm is not addressed? If the answer is really nothing, then that point should not be an alarm. If there is potential consequences, then we're going to look at those and fit them into a categorization, whether it's a low, medium, or high severity. Then we're going to look at the time to respond. How much time does the operator have to respond to that alarm? Based on those two criteria, we're going to set the alarm priority. Then we're also going to talk about, discuss, and document what's the cause, what's the corrective action, and then we're also going to determine the appropriate alarm limit and classify the alarm. All this information, another recommendation of the standard is that all this information should be defined and recorded in a master alarm database. This can be a tool, this can be the control system configuration, it can be an Excel spreadsheet, it can be an Access database, but the idea is have a master record of what all the alarm settings are supposed to be. And as you might imagine, if you're going through and you're talking about what caused an alarm, how much time do you have to respond, what should you do to respond, that information is probably very valuable to the operator. So one of the other recommendations is to make that information available in some way, shape, or form to the operator. best is online through the operator interface, and we'll talk about that more later. So one of the key activities during rationalization is to set the priority. Priority is important because it helps the operator know which alarms to respond to first during an upset. So in the Milford Haven situation where we got 274 alarms in 11 minutes, if they're prioritized, then hopefully the operator can see which are the ones that he needs to look at first and address first. Alarms are prioritized based on the severity of the consequences and the time available to take corrective action. You can see according to this matrix that if the consequences are severe and the operator has minimal time to respond, in this case less than 3 minutes, some people would say that that should be a high alarm. Other people might actually say there's no way that should be a high alarm, that's crazy. There's no way an operator can respond effectively or have a likelihood to respond in time and correctly within 3 minutes. So they would say you need to redesign the system so that the operator is not put in that kind of a position where he has less than 3 minutes to respond to something that could end up with catastrophic consequences. So this is just a recommendation and a starting point, and it needs to be adopted for each individual plant situation. Alarm limits then are set based on the process dynamics. How quickly does the process variable change as a function of time, performance limits, and the time to respond. And on this plot here I'm showing the operator's job. You can think of what the operator needs to do as he needs to detect the alarm or be notified that the alarm exists. He needs to see that it exists. He needs to diagnose what the problem is, and then he needs to take the correct response. And alarm management is all about making sure that those three things occur accurately and quickly in enough time that the consequences aren't reached or the potential consequences don't occur. It's equivalent in the safety world of ensuring that the operator's maximum time to respond is done in enough time so that the process has time to adapt before reaching the process safety time, which is when the hazard would occur. Here's an example of an alarm rationalization tool. I mentioned that these tools help the process to go much quicker and faster. They can build in the algorithms for priority selection and classification and can help you record all that information that we talked about to document the cause, the purpose, the corrective action, which then you can make available later to the operator during runtime. The next stage of the life cycle is called detailed design. It consists of 3 activities: the basic alarm design, which deals with the triggering of the alarms, the HMI design, which deals with the presentation of the alarm to the operator, and advanced alarm design, which deals with potential suppression of the alarms during critical operating scenarios. So let's take a look at these different activities. Basic alarm design is actually one of the stages that affects the creation of nuisance alarms most heavily. So if you walk in a plant and you see that there's a lot of alarms that the operators are complaining about, or there's alarms that are displayed on the console all the time, chances are these are nuisance alarms, and most of the time they're there because poor basic alarm design has been used. Some of the things that are included in basic alarm design is making sure that alarms are not created just because equipment is off. You only create alarms if the equipment is off and that's a problem, or that's not the situation that's supposed to be. It also addresses setting correct parameters such as alarm deadbands and on-off delays, which can be tuned to make sure that alarms only occur when there's truly a problem situation. Now, there's been several studies done by the ASM consortium that have shown that fine-tuning these alarm deadbands and on-off delay parameters has a significant effect on the alarm load on the operator. In some cases, they found to be up to 90% of the alarm load to the operator was reduced just by addressing or properly setting these deadband parameters. So it's a very important part of the alarm life cycle. The second activity in design is HMI design. Again, we're talking about the presentation to the operator. And the goal of the HMI, first and foremost, is to present the information to the operator so he can quickly detect the presence of an alarm. It's all about detection first. And what we want to do is make sure that the state of alarm information is presented unambiguously so the operator can clearly see that there's the presence of an alarm. And now I'm showing a screen. Hopefully it's reacting dynamically, and the question I would ask is, if you look at this screen, the typical operator display, how many alarms do you see? It's difficult to tell. Certainly for me it's difficult to tell. Let's compare this design, which is very representative of the way things are done, to a design that much more reflects the practices and premises related to the standard. Here you can see there's clearly 2 alarms. And what you notice in this case is that the alarms really jump off the screen. So the idea of making it so the operator quickly and easily sees the presence of the alarm is followed in this design. If we think about the differences between the two, we see that the colors yellow and red are being used to indicate the presence of an alarm. The standard does not dictate what colors must be used, because that really differs based on system and culture and region of the world. But what it does say is, if you're going to use specific colors for alarm, in this case yellow and red, then you shouldn't use those colors for any other part of the HMI design. The previous screen we saw that some of the piping and the flow was colored in yellow. That would be a violation of what the standard recommends. We also see here that there's actually multiple ways that we are getting the information for an alarm through to the operator. We're using color, we're using text, we're using blinking, and that's another aspect of the standard which helps deal with the situation with colorblind operators. Studies have shown that between 8 and 12% of the male population is colorblind. So if you're using only color to present alarm state change, there's the potential that the operator may miss those. So the idea of relying on more than just color is important. But here's a summary of what we talked about. Again, you also want to use the most conspicuous colors possible for getting the operator's attention. Alarm summary displays are another key tool that the operator uses to manage alarms. The standard provides a lot of requirements and recommendations on what functions and features should be in those screens. A lot of them that would be related or pertain to the supplier and what they must provide. But there's also a lot of recommendations on how to set it up to make those work the best. One example is alarms are typically displayed on a summary display in chronological order. Human studies have found that operators can best respond to alarms if you keep the high priority alarms at the top, no matter what time they were initiated. So rather than chronologically presenting the alarms, presenting them in priority order helps improve their response. So information like that is in the standard. The third activity in the design stage is called advanced alarm design. You may find that even if you follow all the best practices in the basic design and such, that you're not getting the performance that you want or that you need. And in this case, we move to advanced alarm design, which is where we add layers of logic and programming to control or modify alarm attributes. We may change the set point or the limit of alarms. We may enable or disable them, or we may change the priority based on plant states or things that we're detecting. So some of the common techniques that are used, for example, dynamic alarming or state-based alarming and first out alarming. So again, here we're using some plant intelligence to dynamically change the state of which alarms are presented to the operator based on what we know is going on in the plant. One example of where you might use that, certainly in a batch process, depending upon what phase the process is in might dictate certain alarms are relevant or not relevant, or their set points should be different or limits should be different. But it also is used for suppression. So if you have a big piece of equipment complicated to control, like a distillation column, for example, you can use design suppression in this case to make sure that when the column starts to go unstable, potentially to crash, that rather than present the flood of alarms that actually exist to the operator, that you present only those that are most important, that help them do their job. So the idea of preferentially hiding certain alarms from the operator, given your knowledge of the plant or equipment state, is important to help them respond. Next stage is the implementation stage, and this is where you take the alarms from the design to the operation stage. Testing and training are some of the key activities here, and you can really never underestimate the importance of training to the operators, not only to help them do their job as best as they can, but to make sure that they really buy in and adopt the system. One of the findings from the Milford Haven accident was during the alarm flood scenario, the operators abandoned the control system. They found it to be more of a hindrance than a help. So they felt that the control system and the alarm system did not help them respond or help them do their job. So you obviously don't want that situation to occur. So training and testing and making sure the system is designed to support the operator are very important. Next comes the operation stage, and this is where the alarm is performing its function of indicating an abnormal condition. Operators are detecting, diagnosing, and responding. One of the key elements to talk about in operations is the tools that are available to the operator to respond to upset conditions. And what we're going to talk about here is suppression, which is what you do or what the system may do when you prevent an alarm from being presented to the operator, even though the underlying or base alarm condition is present. And the standard defines 3 different types of suppression. The first is called shelving, and this is a functionality that is typically presented to the operator to use. In this case, the operator is allowed to take alarms that are created or show up on his screen and shelve them, which means temporarily remove them from their view. And it's only on a temporary basis, which means it'll come back in a certain amount of time, 30 minutes, 8 hours, whatever. The idea is that the operator is trying to respond to an upset condition. He's looking at the alarms and he sees that some of them are less important than others, and he wants to get them out of his view temporarily. The idea that they come back means that they won't be forgotten. The second type of suppression is design suppression, and this is when you use control logic, like we talked about, to enable or disable or hide, suppress alarms from operators based on plant states or equipment states or knowledge that you have thereof. The final mode of suppression is out of service. This is really a maintenance activity where the alarm is taken off of the operator's console basically for a long period of time to allow maintenance to be performed. And speaking of maintenance, that's the next stage of the life cycle. And this is where alarms are basically taken out of service for repair, replacement, and testing. Depending upon the importance of the alarm or the criticality of the alarm, you may find that this is a process that really requires rigor. If you've got a safety alarm, for example, you don't want to just take that alarm out of service and not think about the ramifications of not having that alarm. You may need to put in an auxiliary alarm to take the place of it temporarily until that original alarm is fixed. So there's a lot of thought and a process that needs to go into the safe maintenance or maintenance practices and then putting them back into service. In fact, one of the requirements of the standard is if the system provides this out-of-service capability, then the system needs to provide a listing of all the alarms that are out of service, which means you could look before you start up a piece of equipment like they did at Texas City and make sure that all the alarms that are critical to that piece of equipment are in fact ready to go, and you've got none of them on the out of service list. The next phase is monitoring and assessment, and this is where you're measuring the alarm system performance, how many alarms are the operators getting, comparing them to the KPIs that you established in your philosophy and based on what's in the standard. You're also identifying nuisance alarms for the purposes of going and fixing them. And again, this is an iterative life cycle, so when you identify alarm issues in monitoring and assessment, then you're going to set about fixing them and going back through the identification, rationalization, design, and implementation stages. Here are some of the key performance indicators, recommendations as defined in the standard. If we look at and we think about how many alarms can a human really respond to effectively in a 10-minute time period, according to the standard and some of the work that's been done in previous guidelines, such as EMUA 191, it's recommended that you present no more than 1 to 2 alarms on average to an operator in a 10-minute time span to make sure that they have enough time to respond effectively. If you've got more than that, then you increase the likelihood that they're not going to be able to detect, diagnose, and respond correctly and in time. We think about the Milford Haven incident where the operators got 275 alarms in 11 minutes, significantly more than what the standard would call for, and you can see how that would be just totally unmanageable. Now, there are going to be times when you do have planned upsets and you're going to have a lot of alarms generated. If you've got more than 10 alarms in a 10-minute time period, that is considered an alarm flood. And you want to work with the system to make sure that for alarm floods, you're minimizing the amount of time that the system is in flood condition, and you're minimizing the number of alarms that are presented to the operator during the flood. So Milford Haven, again, operator probably would have had a much better chance of responding correctly if during the upset or the flood he was presented with 12 alarms instead of 275. So the idea of making it as manageable as possible is really important. You're also going to measure and look for which alarms are causing most of the traffic. If you find in an unmanaged system, and you typically find this, that there are 10 to 20 alarms that generate probably 80% of the alarm traffic, well, that's only going to get in the way of the operator doing his job, and it indicates a problem with the system, either going back to basic alarm design or a maintenance issue. So the ability to address those will clear up the operator's screen and make it much easier for them to perform the role that they need to do. Another thing we're going to measure is the distribution of alarm priorities. Back in the rationalization stage, one of the things that's suggested in the design process is to make sure that you have no more than 3 to 4 different priorities defined. Again, that has to do with the level of human comprehension to different types of information. So 3 to 4 levels of different priority, and to make sure that you don't provide too high of a percentage of high alarms. It's recommended that no more than 5% of all your alarms be high. This kind of goes into the don't cry wolf scenario. If you've got a whole lot of alarms that are showing up to the operator and they're all presented as high, he's not going to be able to respond to them correctly and appropriately. So you want to minimize that and make sure that it's only the truly high priority alarms that are presented, and then you'll know that they will respond correctly and quickly to them. There are tools to help automate the analysis of alarm performance. This screenshot shows some of the tools or some of the capabilities of the TIPS LogMate tools. So a lot of those metrics or things that we want to look for, these tools provide the ability to generate that information automatically in reports. So you can take that information, look at which alarms are causing most of your traffic, nuisance alarms, and go off and fix them. So these tools help you to automatically create your monitoring and assessment reports and figure out what needs to be done to improve performance and to fix alarm management issues. Next comes management of change. This is very important. Obviously, if even if you followed all of the design recommendations and the best practices, if you don't have a setup for controlling who can make changes to the system and under what circumstances, you're going to shoot yourself in the foot because the system will be changed away from the way it's supposed to be. So the idea here is to set up the practices and procedures for who can change what and when. And it may require review and authorization processes, like if an operator says, this alarm limit, we think there's a problem with it, it's probably too low, this point keeps going in and out of alarm and there's really nothing wrong, then you'd have a committee that would look at that, assess that, make sure that's true, make the appropriate change then, and then update that master alarm database that we talked about earlier that contains the list of all the approved alarms and what their settings are supposed to be. One of the things that's recommended is to compare on an incremental basis, maybe every month, the information that's in that master alarm database, all the alarms, all the settings, to what's actually running in the control system. If you find that there are alarms that are disabled that are supposed to be enabled, or limits that are set differently, or priorities that are set differently than what they're supposed to be, then you know that you have an issue with management of change. The final stage is the audit stage, and this is where you're going to do a periodic review of the performance of the alarm system, primarily to check the practices and procedures, the workflow processes that's being used for alarm management, and your goal really here is to maintain or increase the integrity of the system, of the alarm management system, potentially identify areas for improvement, and if you do make changes, again, you got to go back to the beginning of the cycle and update your alarm philosophy document to reflect any systematic changes that you've made as a result of the audit. Here's an example of one of the tools that might be used during an audit. This is a operator audit questionnaire that we've developed here at Exida to help understand the alarm system performance during normal, steady state, nuisance alarms, etc., generate operator performance. This is very complementary or good to use in addition to the monitoring and assessment, because the direct feedback from the operator is very significant in determining what needs to be changed or what should be changed to optimize the alarm system, so it really works for the operator. So in summary then, we've reached the end of our review of the alarm management life cycle. Some of the main recommendations: obviously take a life cycle approach toward alarm management. Depending upon what state the plant or system is, will determine which stage of the life cycle is best to start with. Philosophy is best to start with if you're a new plant or a new system. If it's an existing system, then probably monitoring and assessment is the best place to start, or audit. Monitoring and assessment, again, will help you figure out how your alarm system is performing, compare it against the benchmarks of the standard, and identify nuisance alarms and determine what you need to do to get back in performance level. It's also recommended to develop an alarm philosophy document, rationalize your alarms so that you're continually making sure that alarms follow the cardinal rule, which is that every alarm requires an operator's response and is truly necessary. It's also recommended to create that master alarm database that you can use to keep track of all your approved alarm settings. Monitoring the performance of your system is really difficult to do without tools, and there are tools that help you do this automatically. So it's really recommended to install these tools to do some automatic monitoring and assessment for you. They'll also help you benchmark against KPIs, and they help you, and they're instrumental in creating a continuous improvement program. In fact, a lot of times these tools will help you identify nuisance alarms, which can be quickly fixed, which if you're looking to embark on an alarm management project, the idea of being able to identify some low-hanging fruit to fix usually gets people excited. When you can identify things that can be fixed or need to be fixed quickly and easily, you can get the operators buy-in to do more and essentially request additional money for funding for alarm management projects. So the idea of identifying low-hanging fruit, fixing that, showing progress, showing improvement, and building upon that is kind of a technique or a secret that people use to get alarm management projects approved. Now, complying with the standard or learning how to follow the standard may seem like a daunting task, but here at Exida we have a complete set of services to help you comply, either in teaching you or educating you what you need to do to take it and run with it, or to help you develop, for example, alarm philosophy documents that you can build from and use. Essentially, we've got the capabilities to help you work with every stage of the life cycle and learn how to comply with it. And again, we're not just talking about complying with the standard for the sake of complying, but really to deliver improved performance. And as I talked about earlier, within the standard is the recipe for how to address all those common alarm management issues. So truly following the standard is the recipe to better alarm management performance. I've listed some other resources and additional information on our website, some white papers and such that have been written. There's a new one coming out in the February issue of Chemical Processing. That's an overview of the alarm management standard, and there's more information on our website. There's also an excellent book written by one of the leading experts in alarm management in the world, Dr. Doug Rothenberg. This book is actually available on the Exida website for purchase. It's 610 pages, so you'll find everything you ever wanted to know about alarm management and more, the details of how to do things, how to do alarm rationalization. It goes into more detail than any other book on alarm management that I've ever seen. So check it out. And also, we are in the process of creating some online training, in particular alarm management. So stay tuned for training classes that'll be available on alarm management practices and principles, alarm management considerations for safety instruments and systems, how to do alarm rationalization, one of those stages that's called for by the standard, how to create an alarm philosophy document, and best practices related to HMI design. So with that, I'll say thank you and open it up for questions. I'm going to look at the Q&A board. And there's a question from Karan that says, when an alarm appears, do you recommend to turn off other data on the screen? And that probably goes into the HMI design element or practice that we talked about. And what we want to do is to make it as easy as possible for the operator to see and notice that an alarm exists. That's the detection part. But we also got to make it easy for them to diagnose the problem and figure out what's going wrong. So the operator is going to need other information, other process information, trends and things are what's going to help him understand what is really going on so that he can take the appropriate corrective action. And also from an operator situational awareness point of view, we want to supplement the alarm indication with the information on the process, what else is going on around the alarm so the operator can make the correct decision. So, good question. Any other questions? Okay, it sounds like there's no more questions then. And I will wrap up and say again, thank you everyone for attending. This webinar will be posted on the Exida website, and please check out the schedule for other webinars, and I hope you'll attend again in the future. Thank you.